Yeah, first of all, maybe I can announce that with the International Building Performance Association, we are endorsing some conferences, some events, some activities. You can keep in touch with the association through the IBIPSA Danube section, and through some contacts on the website ibipsa.org, for instance, or ibipsadanube.org, or through a LinkedIn group. Among the initiatives I was mentioning, we have a newsletter, we have a journal, a scientific journal, Journal of Building Performance Simulation, and we have regional conferences. And besides, we have an international conference which will follow in the announcement in the last slide and in the final part of this conference. We also endorse other conferences. I'd like to mention one, because there is a quite close deadline on December the 18th. It is the High Performance Buildings Conference, which is within a series of conferences, compressor and refrigeration and air conditionings, hosted by the Purdue University and Alex Labs. Here you have references for the website, and you can take a look at it. And as I was mentioning this morning, next conference, next international conference will take place in Italy from in September 2 to 4 in 2019. It will take place in Rome, and we will open a call for papers on April 2018, and the deadline for abstracts will be 30th of June 2018. So that was my announcement. Thank you for this opportunity. And moving to my presentation today, I wanted to start from something we all are aware of, the crucial role of building energy efficiency in the European energy policies. 75% of the existing buildings are considered, according to a recent report from the European Union, as energy inefficient, and only around 1% is the annual renovation rate. It means there is a huge potential for cost-effective solutions for existing buildings. It means a solution that not only optimize energy savings, but also the global cost of the investment. We have to do that trying to preserve or improve indoor environmental quality and specifically thermal comfort, because typically when you renovate a building in our climatic regions, you may face problems of overheating. And this is really important, especially in climatic conditions or in contexts like the Italian ones, where we have cooling demand, which is only 10 to 15% the heating demand, and just one building out of 4 is actually meeting its cooling needs. So we need to preserve this opportunity of having buildings running passively according to the summer behavior. So we have actually 2 objectives when it comes to design a building retrofit. We have first aim, which is improve the energy performance, and the second goal is limit the global cost of the investment. And so we have to perform a multi-objective optimization. Multi-objective optimization can be done by means of simulation tools and optimization algorithms. A simulation tool allows us to also to check comfort conditions, and so to put some constraint in case to discomfort conditions. But when you have two competitive goals, what you get when you analyze all the possible configurations for the renovation of the building is that you don't have an optimal solution, a single optimal solution. You have a range of optimal solutions, which are the solutions which came at the lowest cost for a given energy performance. So in blue here in the corner, you have the optimal solutions, which is also called the Pareto front of this group of solutions, and which range from the cost optimal solution, the solution which in absolute has the minimum cost, and the energy optimal solution, which is the one who, which comes at the minimum energy consumption. So the idea of our contribution here today is to discuss the composition of these solutions in terms of energy, of mix of energy efficiency measures. So we want to analyze, we want to suggest some techniques to analyze this Pareto front. And to do that, to show you how we try to address this task, I wanted to focus on a set of simplified building modules. They all are based on a common shoebox-like module, square floor, 100 square meter, 3 meter high, with a very poor insulation for the opaque envelope, single pane glass and timber frame for the windows, standard boiler, radiators, non-off control system, and moderate insulation for the distribution system. We introduced some variants to this basic module, assuming different compactness ratios as representative of different archetypes. 0.3 for a kind of intermediate floor unit, 0.6 for a kind of penthouse, and 1 for a semi-detached house. 1 or 0.6 or 3 is the ratio between the exposed surface and the volume of the module. And we also analyze what happens if we have all the windows towards the east or facing south. We repeated the analysis for this set of 6 reference buildings for 2 different locations in Italy. Also, those Milan and Messina are representatives of the wide range of conditions that you can have in Italy with longer or heating-dominated climates for Milan or cooling-dominated climates for Messina. We then classified the possible energy efficiency measures in 4 groups. The first one is related to the insulation of the external envelope. We have the option of insulating differently wall, roof, or floor, vertical walls or roof or floor in thicknesses from 1 to 20 centimeters in step of 1 centimeter. We consider 4 options for the replacement of the windows with an improved frame and with 2 double glazing system or 2 triple glazing systems, differing one from another based on the solar decay coefficient. We can have one kind with a high and one kind with a low solar decay coefficient. For the renovation and replacement of the heating system, we consider just the replacement of the boiler with a modulating or with a condensing one. And finally, we analyzed the possibility of adding a mechanical ventilation with heat recovery system. If you analyze all these interventions and you combine them, you can get up to more than 270,000 different combinations. It would take 192 days to simulate all those configurations, considering 60 seconds per each. So it is necessary to work with an optimization tool, a kind of algorithm that is able to run some simulation and to understand where to explore the space of the solutions in order to achieve the same goal with just a reasonable time. So in 3 days, in this case, we were able to get the Pareto front for one of those configurations that I discussed. So the final result of this simulation are those groups of points that you can see here for Milan and Messina and for the 3 different aspect ratios. Here the plots are considering the east orientation for the windows, and in different colors you have the different aspect ratios. This group of points are the optimal solutions, and so you range for each of this group of colors from the cost optimal to the energy optimal. And we repeated the same analysis for the south orientation. Now when it comes to analyze the composition and the impact of each of those intervention measures that I described, you can do it very differently. You can start from, for instance, a single configuration, and you can zoom on the points in the Pareto front, and you can use a parallel axis plot to represent the levels of the different intervention measures in each of the solutions. So you have here the level of insulation for the vertical walls, for the roof, for the floor. You have the kind of windows that we have used to replace the original one, the different options for the boilers, and the 2 possibilities for the ventilation, natural ventilation or mechanical ventilation. Right. And you can start with, for instance, you can start with the cost optimal solution and see that it comes from the use of a significant thickness of insulation and from the replacement of the window with the double glazing high solar gain coefficient 1, and you move towards the left, so towards higher efficiency, energy efficiency solutions, but also towards higher costs, adding some insulation or in correspondence of some discontinuities, you have different technical solutions. For instance, here you have triple glazing, and farther on you have the replacement of the heating generation system. And finally, when you move to the last group of solutions, in the upper left part of the chart, you have the mechanical ventilation playing a role. Clearly, it is quite complicated to analyze each of the Pareto fronts this way and compare them. And so what we were suggesting is to analyze the frequency distribution of each of the intervention solutions in the Pareto front. So you can focus on the frequency distribution charts on the diagonal of this scheme, and you have here the frequency distribution for the thickness of the insulation, the frequency distribution for the different kinds of windows or of the different boilers or ventilation system. You can use the same approach to analyze the performance, so the energy performance and the net present value. Nice thing in this sketch is that you can combine different plots, as we did, reporting each of these solutions in the Pareto front in terms of 2 coordinates, which correspond to 2 possible groups of intervention measures. So this way you can, for instance, study the interactions between different intervention measures. To give you an example, we can focus, for instance, on the heating system, on the boilers, and we can check the case of condensing boilers that is, in this case, represented by these points on the left of the charts, on the right of the chart, sorry. And for instance, condensing boiler are used in combination with high insulation levels, with triple glazing, with high solar gate coefficient, with natural ventilation, and of course, condensing boilers can provide very low energy needs and medium to high net present values, so medium to high costs. You will find similar plots for all the configurations in the proceedings in the paper, but based on that and for time reasons, I focus mainly on the distribution of the energy efficiency measures in the Pareto solutions. So we can move to a first table, first conclusion table, in which I analyze the presence of each of the intervention measures inside the set of solutions in the Pareto front. So we can see, for instance, that double glazing with high solar gate coefficient is always an option inside the solutions in the Pareto fronts for all the locations, for all the configurations, and for all the orientations. While, for instance, single glazing, so no replacement of the windows, is an option just in the case of the climate of Messina, the warmer climate, and for south orientation. And you can see, for instance, double and triple glazing with low solar gate coefficient are almost never selected. And so on. You can study boiler replacement and ventilation. You can see when those interventions take part in the Pareto solutions. More interestingly, you can maybe analyze the two extreme points in the Pareto front, the cost optimal. You can use again a parallel plot to analyze what is going on in this kind of solutions for different configurations. This is the case of Milan with the smallest aspect ratio, 0.3. For south and for east, you can see you deploy significant insulation and you replace the window system. You do the same or almost the same for all the other configurations, but for instance, in the case of Messina, you never, and south orientation, you never need to change the window. You always rely on the insulation. Besides, cost optimal solution never use mechanical ventilation, and you never replace the heating system or the boiler. So using the same table, you can see those relations, those contributions from the different interventions. Here you have also the thickness of the insulation that is needed, but mainly you can see that cost optimal can be obtained just using an appropriate layer of insulation and replacing the windows with a double glazing with high solar gate coefficient. And with the exception of Messina, this works for all the Messina for south orientation. This works for all the configuration that we have analyzed. And you can do the same for the case of the energy optimal. In this case, you need to use some other measures. And particularly mechanical ventilation is generally an option. And triple glazing is also a preferred solution. It changes a little bit for the smallest aspect ratio for Messina. Here you don't need mechanical ventilation and you don't need triple glazing for south. But then when you move to the largest values for the aspect ratios, you have a similar profile in the plot, meaning that the configuration is very similar. And again, we can summarize the outcomes, taking a look at the final table here, where you see that energy optimal are given by the use of very high insulation level, replacement of the windows with triple glazing, high solar gate coefficient, The only exception again is Messina for south-oriented windows. You need to replace the boiler just for the higher values of the aspect ratio, and you use a condensing boiler, and you almost ever use mechanical ventilation. Again, the only exception is Messina with the most compact aspect ratio 0.3. So this way you can imagine how you can work when you have to optimize building retrofit, but you can also maybe try to give some suggestion to the subsidization policies. You can see that some kind of technologies are never contributing to the final goal, and so maybe you can focus your efforts on some of the techniques and some of the solutions that we have described. Of course, this is just a suggestion. We didn't consider other possibilities, other solutions. We, for instance, neglected the applications related to renewable energy sources, but this was an example to give you an idea of potential of these techniques and of those approaches. Thank you very much.